Okay, so before the midsem we finished this proof that formulas and WIT3 ABPs are equivalent models, but you cannot reduce formula to WIT2, although WIT2 ABP you can convert to a formula. And interestingly, if you relax the computation definition to approximative complexity or approximative circuits or approximative models in general, then you can get even formula and WIT2 ABP as the same model. Okay, but in this, with this bar, so this denotes the border of your algebraic model. Any questions about that? Okay, so then we will start a new topic, which is proving lower bounds. So there are several theorems that prove interesting polynomials like determinant or permanent cannot be computed if you have a restricted model. Determinant, of course, you know, can be computed in VP. Computation of permanent is still an open question, both algorithmically and in the circuit sense. It is believed to be not computable by circuits of small size, but there is no proof yet. So the proofs that I will present will be for restricted models. Okay, some resource will be restricted, and then we'll show that determinant, permanent are impossible to compute. Usually in these proofs there will be no difference between determinant and permanent. The same proof will hold for both, which will also be a bad sign that these proofs cannot separate permanent from determinant. Okay, so that is the current status, but there are many techniques that go into this, so we'll do that. Current result that we will discuss is also to do with depth reduction. So we'll in particular prove something about depth 3 circuits over finite fields. Okay, so in particular we will show that determinant complexity in the depth 3 model over finite fields, where think of Q as a constant. Okay, Q is not growing, so field size is actually fixed to an absolute constant size. In this model, determinant actually requires essentially brute force size, which is 2 raised to degree, 2 raised to d. Okay. What happens if you change the field to complex? What is the complexity of determinant in the depth 3 model? That was around d raised to square root d, right? So that shows you a gap between the fields. So when the field is very small, then determinant will need brute force size, but if the field is large, then determinant can be computed by depth 3, which in particular means that depth reduction cannot be done to depth 3 for small fields. Okay, so this actually will be saying something about the optimality of the depth reduction as far as the field is concerned, which is a bit surprising, right? So it is surprising that coming to depth 3 really requires the field to be large, otherwise that proof will not work provably. So background is, recall that reduction to depth 4 always works. It works for any field f, but as seen in the proof, reduction to depth 3 requires at least large characteristic. So it requires the characteristic of f to be um, bigger than the multiplicative Fannin's involved in depth 3, right? So that was around square root d, I think. Was it? When you come down from depth 4 to depth 3, yeah, I think it was square root d. So omega square root d. This was because of the Reiser-Fisher formula. So to apply this Fisher's trick, converting x1 dot dot xn to sum of powers of linear polynomials or even linear forms even. So that actually you get 1 over n factorial there. So you need the characteristic to be bigger than n, which actually boils down to square root d, because that was the sigma pi model. The two pi's were around square root d. So we had asked this question: can we do reduction for other fields? For small characteristic. So at least when the size is small, then we will give a proof that this is impossible. Okay, so that is what we will show, which will suggest that you have to be mindful of the field. You cannot hope to get to depth 3 without field assumptions. Yeah, so this seems to be smooth development, but the lower bound proof is actually very old. It is much older than the depth 3 reduction. Okay, so this was done by Grigoriev, Karpinski. So this will say that over the field FQ, determinant d cross d or permanent d cross d well, or as in this is and, it holds for both. So determinant requires depth 3 circuits of size 2 raised to omega d, where the constants involved in omega, big omega, depend on q. Okay, so there is a q here that refers to the constants which are involved. So as long as q is constant, it doesn't matter that this is just 2 raised to omega d. But when q starts to grow with d, then this result actually has no meaning. It's not interesting. Okay, so it is interesting only for constant q, because the constant involvement is, as you will see, it will be large. The dependence on q will be large. But think of constant q and then it's fine. Or q may grow very slowly with d. Till that it will be fine, but not for general q. So it's really a constant q result. Right, so before we go into the theorem proof, note that if there was a depth reduction, so note that for permanent already you know a 2 raised to d size circuit, depth 3. by Reiser's formula. For determinant we don't know, the best we know is well, okay, we know because it's this for other fields we know. No, also for permanent, for small fields we don't know. Do we know 2 raised to d sized? So originally when we had shown permanent is in VNP, right, or determinant is in VNP, that was, were we dividing by some constant like 1 over d factorial?
So determinant originally we had.
Determinant is
Newton's formula.
Yes.
No, not Newton formula. That is much more advanced. Just the simple fact that determinant is in VNP. Just that fact. Or permanent is in VNP. So did we divide? Probably. Yeah, probably that was not used. Division was not used. So for one of them we have this 2 raised to d depth 3 circuit for any field, but anything better than that, like for determinant better than 2 raised to d, that only came through depth reduction, that did not come algorithmically. So if there was a depth reduction for determinant, d cross d determinant to depth 3 over FQ, then the way our depth reduction result was, the size would have been d raised to square root d, which is much smaller than the above. Right, so this d raised to square root d is much smaller than 2 raised to d. So that would have contradicted this theorem. So in simple words, the theorem rules out any kind of interesting depth 3 circuit for determinant or permanent. 2 raised to d is possible, but nothing below 2 raised to d. Yeah, although the monomials are around d raised to d. So 2 raised to d is slightly smaller than d factorial. Which comes by definition. So in this sense it is it's an optimal lower bound, right? This 2 raised to d we would say is a nearly optimal lower bound for depth 3 circuit size for determinant or permanent. So the proof will be long and it will be a long and hard road. Okay, it will take several lectures, maybe we can cover in 2 lectures, but there are many ideas. So do you understand the statement and the comparison? So all these lower bound proofs will be almost all of them will be fairly technical, and several kinds of ideas will be thrown at you together with calculations. But that is expected. Okay, we don't expect this to come cheap, if it comes at all. Okay. So here the basic idea will be, well, so what do you think would be the idea to prove such a thing, that determinant or permanent requires brute force sized depth 3 circuit? What do you know about depth 3 circuits to be able to wish such a big result? Well, you know that it is a sum of products of linear polynomials, right? So you have to prove something. If you can prove some strong result about just product of linear polynomials in a way that generalizes to their sum also, right? If you can find such a property, then maybe you can use that property to prove that determinant and permanent are hard. Uh, so, so that property would be related to rank of some associated vector space. So, for a product of linear polynomials, we will associate a vector space and we will look at the rank of that, and this will actually generalize naturally also to sum of products of linear polynomials. So, it will be then rank of a depth 3 circuit, okay, rank of an associated vector space. So, we have to show that this rank for a depth 3 circuit is large or small.
Small and then get.
Right. So, you want, idea would be to show that this, well, first you have to define this vector space and its then rank will be defined, and you have to show that for the computational model it is small, while for the target polynomial it is large. And if there is sufficient gap, then asymptotically you have proved you have a lower bound, you have an impossibility result. So, yeah, and somewhere magically this q being constant is used, right. So, fq will be used in this implementation in a very crucial way. So, fq has q elements, think of q fixed and independent of d, that is what we mean by fixed. Okay, with respect to d it is constant. So, to define determinant or permanent you only need d and fq. So, think of these two as independent parameters where q is fixed and d is growing, d grows to infinity. D, think of d as the input size, and let C be the model. So, C is a sum of TIs where each TI is a product of linear polynomials. So, what could be the notion of rank of TI? So, for now I am not defining the vector space, that we will do later. Let us just define rank to be rank of the linear polynomials that define TI, right, whose product is TI. So, rank of TI is just rank of the linear factors over the field FQ. So, when you look at a product gate where this rank is very small, right, what does it mean? Say this rank is R. So, that means in some sense TI is R variate, right, because these, so if you look at the basis of the linear factors, R of them are independent, but other ones actually just a linear, they are just a linear combination of these L1 to LR. So, it is as if TI is R variate, where the variables are L1 dot dot LR, right. So, if R is very small, then TI is a low variate polynomial. If R is large, then TI is more of a general number of variables. So, small rank TIs are actually, in this sense, they will not pose a problem. They seem to be quite weak when the rank of TI is small. So, what should we do when the rank is large, right? Those are the TIs whose where there is more complication. So, our proof will always be in these two cases, TIs with low rank and TIs with high rank. So number of variables is d square. D is the degree of the determinant, d by d determinant, and let's use a parameter tau. It will be around d, constants depending on q. So we'll make tau specific towards the end. So the cases are like this: a low rank TI, say rank of TI is sufficiently small, so tau over 10q. So this has low rank partial derivatives. So partial well, when you look at the partial derivatives of a low rank TI, since TI is just a polynomial in L1 dot dot LR where R is small, so if you look at the set of all the derivatives, right, their rank will also be, the rank of that space will also be small, where small is really being overused. I mean, R small and the dimension of this derivative space, these are different. So we are talking about low in two different ways, but it will be low compared to when R is large. So if R is large, then this partial derivative space has actually much bigger dimension. So we'll ultimately be looking at the vector space will be the vector space generated by the derivatives. Okay, that is the, let us say that is our measure. So for the algebraic model, we will define a measure which will basically be the dimension of the partial derivative space. So when R is, when rank of TI is small, then this measure is small, and when this is high, so a high rank TI say rank of TI is greater than tau, so naturally its partial derivative space will be large. So is there a way to force this to become small? I mean, so we are looking at a polynomial where the derivative space is large. So what should you do to make it small? Yeah, you kill some of the extra variables. So how do you kill them? You kill them by evaluating them at points. So to handle these, what we will do is we would like to zero them out. So a high rank TI we would like to just completely zero out. Okay, which will be done by picking a random evaluation. So why would a random evaluation work to zero this out? So to see this in the simplest possible way, think of x1 dot dot xn. So what is the probability that this product vanishes? You just have to pick 0 somewhere, right? So what is the chance that x1 dot dot xn is picked to be 0? So x1 is picked to be 0 with probability 1 over q, right? So accordingly you can calculate the probability, and as n grows, you will get more opportunities to set the monomial to 0. So this is the intuition that these high rank TIs, since they have many, they depend on kind of many variables, So this L1 to LR, this R is big. So since it depends on R many variables where R is large, you have more chance to actually just zero this out by random substitutions. This chance is actually smaller if if it had fewer variables. Okay. But those cases are anyways easy for us because those TIs will have low rank partial derivatives. And on the other side, when the variables are many, then actually by evaluating them randomly, we'll set them to 0. So this green things will be gone, only the blue will be left. And so we would have essentially proved that in some sense, the circuit has low dimension of the partial derivative space associated to it. So this will be the upper bound on the measure of the model, right? So and then once we have done this, we have to show the opposite for determinant. That if you do this rank of partial derivative space analysis for the determinant, that comes out to be large, right? So determinant cannot be computed by this model, right? That is the overall proof idea. So prove upper bound on the model and lower bound for determinant. Okay, so that will be the overall strategy. But implementation of this will really go into gory details. Okay, this is not an easy proof, but the idea. Do you understand this overall, this very vague idea? So as we are associating, defining a measure. So the measure for determinant polynomial we'll show is large, and the same measure for the circuit model will show is small. So the measure will distinguish determinant permanent from the model. Okay. Right, so this motivates. So let us do this now explicitly. Right, so this description motivates the definition of a matrix corresponding to, actually it will be for any polynomial, so to any polynomial so we want to define a matrix for a given polynomial C. Okay, so this matrix is essentially we'll just look at the derivatives of C, make them our rows of the matrix, and in every row that particular derivative will just be written as what? We'll write the evaluations of that polynomial, picking some points in the space fq to the n. Okay, so the matrix will be basically the rows are indexed by derivative operators and the columns are indexed by evaluation points. So because the above proof suggests both of them. So the blue part suggests that you have to use derivative operators, and this dark green part suggests evaluation points have to be used from fq to the n. So we'll use both of them to define the matrix. So this is the following matrix. For C, the matrix is MKC, comma A is the subset of points. So, as promised, the entry here is differentiate or derive on C at the point A bar, where the rho is derivative with respect to alpha and the column is point A bar. So the rows are basically k ordered derivatives. Okay, think of alpha as the exponent vector. The variables are x1 to xn. So on the variables there is an exponent vector alpha bar, and you want to only look at k ordered derivatives, which means that the sum of these exponents is exactly k. K also will fixed later, and the columns are, they denote some points in the space. So points in some subset A of fq to the n. Right, so just looking at this definition, you can see that the space has to be finite, at least the subset A should be finite. Why should the field be finite? So that actually comes from this intuition of x1 dot dot xn vanishing, right? So if the field is quite large, then x1 dot dot xn will not tend to vanish, because the chance of hitting 0 in a big hay of points is negligible, right? So that is the problem. So you don't want the field to be too big. If it is too big, then x1 dot dot xn is negligibly, I mean it vanishes with a negligible probability. So the probability looks interesting only when the field is small. So in that finite space, we will be picking some subset A, and then this matrix gets fully defined. So this matrix is just derivatives at points. That's all we are doing. So where we'll take k to be tau over 10q. Okay, so once we have fixed tau, this will also get fixed. So this k is our measure of basically low rank product, Ti. So we had used this before also. This will be the k, and E shall be the set of evaluations or evaluation points on which each derivative for high rank Ti vanishes. Yeah, so we want these points A bar to be such that this high rank TIs don't contribute in the calculation. But there will be more restrictions on A, which we will put as we go through the proof.
We are picking them randomly, right?
No, so yeah, in the proof we will be picking them, we will show the existence of A such that the upper bounds and lower bound properties hold, but in the end A will be it will be a defined subset. It is not a probabilistic object. So probability will be used in the proof to show the existence of it. I mean, the proof can remain existential. It's a lower bound proof, right? So existential proof is fine.
When you show the determinant does not have this rank,
Right.
then you should go through all possible A's such that.
No. You want upper bounds and lower. You want a measure. So the measure will be defined by A. Because this MK C, A is the object you are measuring.
Once you show for a nice A, you can show for that A irrespective of, I guess for
Yes.
that A, every circuit is low measure, and for that A the determinant is high measure.
Exactly. Right. So this measure will be, I mean, we could say safely at this point that the measure will be existential, because at least in the proof we will not work out the details what exactly A is. We will be happy with an existential measure, because as long as a measure exists that separates model from determinant, we are fine. We only want a lower bound proof. There is no demand for an algorithm here. So we will be preferring probability in the proof, but that may not be very important mathematically. It's just for convenience, I think. Right. So once we have fixed K and A are fixed or defined, we say that we have a measure on polynomials F, which is the rank of this matrix over the finite field. So we will say that this gamma, which is the number associated with the matrix. This matrix is huge, exponentially large, but there is a single number attached to this, which is gamma F. So this is a complexity measure of polynomials. So it will be defined for all the polynomials with coefficients in FQ. And again, so in the end we want to show that gamma on C is small and gamma on determinant or gamma of permanent large. Okay, so which means that C cannot be equal to determinant. That is the strategy. So first we will do the small part, later on we will do the large part, largeness part. Okay, so let us first do this upper bound or the smallness property. Yeah, so already this lemma 1 showing that gamma C is small, right, that already is an achievement, because you have identified a measure that is small for the circuits, right. For depth 3 circuits, this is a measure that is small. Already finding such measures is a challenge. So by definition, one measure is the size, right, but that is not very helpful, because that is exactly the thing you want to prove is large for determinant. So you have to find an alternative measure and finding this alternative measure is a challenge. Okay, it requires creativity to come up with an alternative measure that is small, and that is not size. So it should be more mathematical. What we will show is that for all tau and k at most tau over 10q, there exists a subset E of fq to the n of size almost everything. So the whole space is of size q to the n, and this subset E is of size q to the n times something. Well, this something will I want to make it small, so it's not nearly everything, but much smaller. So the basically subset E over q raised to n is quite small. Okay, it actually is tending to 0. So we identify a small set E in the space such that the definition of A will be the complement. So think of E as the error set. Okay, these are the bad points. So apart from these bad points or these error points, A is almost everything in the space, and for this you use the measure. So gamma k comma A of C is less than SQ tau. Right, C is your depth 3 circuit. This is sigma Ti. So the measure on sigma Ti is, well, I am saying small, but it seems to be S times q to the tau. So it will really depend in the end. What does small and large mean? But let me continue with the highlight that this is small. Okay, so because it is certainly less than, it's a inequality in the correct direction. So we will show that gamma of C is smaller than SQ tau. Later on we will show that for determinant this is far more than SQ tau. Okay, so the two things will be enough to finish the proof. Right, so actually looking at this part, I want this to be very small, in fact tending to 0. So which suggests that in the end tau should be picked as let us say q log s or 8q log s, right. So if you pick that, if you pick tau to be more than that, then this multiplier is very small, and correspondingly the set A is nearly everything.
Tending to 0 with what changing?
Well, the only thing changing is n or d. That is the only variable allowed to grow.
You want tau to depend on n, right? In some way.
For sure, yeah. Yeah, so q log s means that it is growing.
So here S is a parameter, right? It has nothing.
S is a function of d. S is a function of n. S is the size of depth 3 circuit. I mean, S is at least d square, because d square is the number of variables. Well, okay, maybe there are some inaccuracies, because S I am saying is the number of TIs. But yeah, I mean, truth be told, S will be at least n. You can show that. You cannot. There is an easy proof that if you use less than n product gates, you cannot, the sum cannot be computing determinant of permanent. Those are easy proofs. So even in this definition, S will be a function of n, growing function of n. It cannot be too small. And then tau is a growing function of n. Yeah, but what may not be clear is why we need q to be constant. That I think is not visible here, but we'll see that at some point. Okay. Any questions about the statement? So let us go through this. So to upper bound gamma for C, it suffices to do it for T1. Is that clear? If we show that the measure on T1 is q to the tau, then we get that measure on C is at most S times that. Why? Oh, sub-additive I have to define. Well, first of all, yeah, so if you know that rank of T1 and rank of T2, well, this measure gamma actually. If gamma of T1 and gamma of T2 you show to be small, then you can deduce that gamma of the sum T1 plus T2 is also small. Right? This happens because if you look at the definition of gamma, it is rank of a matrix. So you have basically a matrix for T1 and a matrix for T2, and both are low rank. So the sum is also correspondingly low rank. Okay. So we will only work with the product then, which will simplify things by a large amount. So this is because of, so what I just said is called in one word sub-additivity. Why is it not called additivity? Yeah, just because of the unfortunate fact that rank of A plus B may be matrices A and B, rank of A plus B may be much smaller. Right, an example is exactly A and minus A is a good example. So we'll just, but we only need sub-additivity, don't need strong additivity. So because if you look at f and g polynomials, gamma of the sum is upper bounded by gamma of f and gamma of g. Okay, so let's leave this as a linear algebra exercise. Okay, so let us now work with T1 being a product of big D many linear polynomials. Right, and we have, so now we want to study gamma of T1 basically, and this proof we'll do in two cases as already suggested in the original idea, that one when L1 to LD their rank of the linear polynomials is small versus when it is large. So in both the cases we'll show that the measure is upper bounded by q raised to tau. So for low rank, let's use blue. So the case when rank of, let's not use T1, just T. So rank of T is less than equal to tau, right, in this case. So let L1 to LR form a basis for L1 to LD. Then T is an FQ linear combination of these products L1 dot dot LR, E1 to ER are the exponents, and how big can EIs be? Less than? Yes, but if I allow that, then your upper bound will come out to be D to the R. It will come out to be D to the tau, which is hopeless, because Q is constant. You want Q to the tau, not D to the tau. Right, so that is a problem. Even in this case, when the rank of T is small, just because the exponents in L1 to LR may be large, there are just this set M has too many monomials, has too many products. So what should you do? What should be the correct definition of M? Yeah, so you actually have to look at EIs mod Q. So EIs will be actually less than Q. Why is this allowed? What happens if you have L1 to the Q? Well, I say that L1 to the Q is L1. Is that fine?
Sure, because you're going to be evaluating it at point.
Exactly. So the definition of gamma is based on the matrix, and in the matrix MK, you are actually not looking at the entries are not polynomials; they are just evaluations, and the evaluations are happening in the space FQ to the n. So you should not think of L1 as a linear polynomial. It's actually, when it is used in the matrix, it only gives a field element, and for the field element raised to E1, you will just get L1. Okay, so that actually is one important part which was not discussed in the basic idea, that when the rank is small, you also have to use the fact that the exponents are small, so that the overall monomials or these products in M are few. Okay, so now you can get Q raised to tau. That's the upper bound. So because since definition of gamma only depends on the evaluations of T, in FQ to the n or on. Fine. So what this means is that irrespective of A that you pick, so irrespective of measures, the gamma Ka of T is upper bounded by the size of M. Right, this should be clear because of number of columns in the matrix. No, not number of columns. How do you see this? M is the set of possible products of L1 dot dot LR, all possible products. So T is actually a linear combination of these monomials, these products. So I guess you again use the subadditivity property, and yeah, so this is again the subadditivity property.
But then this is the basis for T, but then you're differentiating it too, right? So no, but
Subadditivity again. This is again the subadditivity property. That's why you get this. So subadditivity will reduce gamma to just this product, and gamma of this product is what? Is it 1?
why will you get?
Why doing that?
Yeah. So like he said, why is it just not M? Because even after you differentiate these,
Exactly.
these will form a basis
Exactly.
for the rows.
So done, right?
In fact,
Yeah, so you differentiate it k times.
But then still you are in that same shape.
Sure, okay.
in fact, it probably will be lesser than F, right?
Yeah, doesn't matter.
But yeah.
Yeah, that is needed. Even with the subadditivity, that's needed. That M is this dou equal to k on M is a basis. Gives a and so the basis size cannot exceed size of M. Is that clear? And size of M is simply q to the r, which is q to the tau. See, so just what we wanted to show. So next case is high rank case. So now r is greater than tau, and L1 to LR spans L1 to LD. So we cannot use the above proof because this proof in blue use the fact that q to the r is less than or equal to q to the tau, which now doesn't hold. It's much more than q to the tau now. So this is the part where we'll use speciality of A, this subset A. Which will require definition of the set error set E. Okay, so till now this blue part holds for any A. So that luxury will not have anymore. So we'll actually fix A probabilistically. So for each non-constant Li, we have, so we, I mean, as discussed in the initial idea, we actually want to just kill T. So when T is evaluated on points in A, then it should just vanish, right? So that will boil down to studying whether L1 vanishes or not. So probability that L or Li vanishes or not, that Li vanishes on a randomly chosen A bar in the space. What is that?
1 by Q.
Exactly 1 by Q, because Li is non-constant, hence non-zero also. What is the proof of this?
true, sir. All but one variable is a unique value of the last.
Exactly. So you know that there is at least some variable in the support of Li, say x1 appears. So just keep x1 free and fix everything else, and that will fix x1. So except this value of x1, Li will not vanish. So the others were fixed randomly. Ultimately, the probability comes out to be only 1 over q. Right. So here we are using the fact that q is it's a finite field. Actually, previously in the blue part also we used this when we reduce the exponents mod q. There also we use the fact that evaluations will happen from in this finite field. Okay, so this immediately gives you that expectation over choices, random A's, number of I's such that Li A bar is 0. What is this expectation? How many Li's will vanish? There are R many Li's, right? So R over Q, which is greater than tau over Q. Yeah, so now R is greater than tau, and that actually is what helps us in saying that if you have a random point chosen, then expectation of something vanishing is pretty good. Well, or the probability of something vanishing is pretty good, and the expectation, because the expectation is good. Expectation is far more than 1. Okay, so let's look at this probability then. So the probability over A bar that the number of I's for which Li A bar vanishes, this number is smaller than k so basically what is the chance, looking at the expectation, what is the chance that this count on I for which Li is vanishing is less than k?
By 10 e to be Markov, right? You are using
Chernoff has to be used. Yeah, so Chernoff is the correct bound. So if you have not seen it, then let's write down the statement of Chernoff bound. So Chernoff bounds the probability of a random variable x, which is a sum of 0, 1 random variables xi's. So I don't need the sum here actually. I just need mean and I just need the mean of x, which is mu, let us say. So probability that this random variable is far away from the mean. Okay, so this is mu x, mean of x. So probability that it is some multiple ahead of the mean, or it is sufficiently smaller than the mean, so minus. Okay, both these events or any of these events, that x is either on the right side of the mean or on the left side of the mean, these probabilities respectively are up small. So how small? It's like e to the delta mu. Yeah, let me give the expression first. So in this expression here, so we are anyways interested in the things happening below the mean. So in that case, what this is saying is that the probability that the random variable is much smaller than the mean, okay, this is kind of e to the minus delta mu. Okay, so e raised to minus delta mu is a fraction, so the probability is very small. So if you keep increasing delta, or this delta times mu is the difference, right? So if you keep going away from the mean backwards below the mean, then the probability will be also falling accordingly, e to the minus difference. Yeah, and for the 1 plus delta thing also, this probability can be made smaller, but anyways we won't be needing that. But Chernoff bound basically gives you bound on both sides of the tail. Okay, so being on the tail sides is the probability is very low. You can read the proof of this, or well, you can try to prove this. And easy way is just read the proof on Wikipedia. Will not take much long. Okay. Yeah, so coming back to this green line, so probability that number of i's such that Li vanishes at randomly chosen point a bar is the number of i's is smaller than k. This probability is small. Okay, this happens with low probability. So I mean, so why are we proving such a strong thing? In the initial proof idea, I had said that, well, one of the Li's will vanish with high probability. So why do we want here that, why are we looking at whether key of the Li's are vanishing or not? It's not one, but we are now actually looking at key of the Li's, right? Why do we do that?
You want like entire columns of the matrix to become 0.
Because we are using derivative operators of key order. So suppose there are k plus 1 Li's that are vanishing. So when you will apply the key order derivative, it will continue to vanish. Okay, so we actually want we not only want t to vanish, but since we have used differentiation, key order differentiation, we actually want the derivatives to vanish. So derivative vanishing will need that many repeated zeros in t. So we are actually, this is why we are comparing number of i's with k. And since this is low probability event, okay, we should now be able to deduce what we wanted. So let epsilon t or Et be the a's in the above low probability event. So then A bars that are not in Et, it makes greater than k Li's zero. Okay, so Et are these bad A bars, but other than the bad A bars, the k plus 1 of the Li's will vanish. So for all A bar that are not in the union of Et, and these are the T's of high rank. So I mean so there are many, if you look at the level of the circuit C, then there were many TIs, and look at the ones for which the rank of TI is more than tau. So for those, take the union of their bad A bars, this is still a small set, right? So outside this, if you pick a bar, then every key derivative vanishes. So dou equal to k is not a single derivative operator, but all these possible k order derivatives. So pick any k order derivative and pick any such t, and any point a bar that is not bad. This is 0. Okay, so let me stop here. We'll finish the calculations tomorrow.